Hi guys, today we're going to learn about arcs and chords. So if you take a look at our first picture here, we are going to learn three theorems today. So in our first picture here, we have a circle, we have two chords, and we have some arcs. So let's take a look. TU is a chord, RS is a chord. What happens in this theorem is if TU and RS happen to be congruent, then their corresponding arcs are congruent. So arc TU would be congruent to arc RS. So let's write down what theorem 1 says. Okay, so in a circle, if two chords are congruent, then the corresponding arcs are congruent. And vice versa. If the arcs were congruent, then the corresponding chords would be congruent as well. So a lot of today, there's going to be a lot of setting things like equal to each other. Not everything, but a lot of things you'll be setting things equal to. So let's take a look at number 1. First, I notice that my chords, I have 13 and 13, so they are congruent. And then we take a look, I have corresponding arcs, TU and WV. They want to know how much X is. So if these are congruent, we know the arcs are congruent. So this is a nice and easy one. X is going to be 79. All right, so let's take a look at number 2. Number 2, they tell us that our arcs are congruent with the tick marks. So if the arcs are congruent, that means that our chords are congruent as well. So if one arc is 36 and the other one is 2x minus 12, let's just set them equal to and solve. All right, I'm going to squeeze this in over here. So 2x minus 12 equals 36. So let's add 12. Add 12. 2x equals 48. Divide by 2. X equals 24. All right, so if we take a look at number 3, so we do have two chords that are congruent. They actually happen to touch, so it makes it look like a different type of problem, but it really isn't. These chords are congruent. So if these chords are congruent, then their corresponding arcs are congruent as well. So AB and AC are congruent. So if AB is X, then AC happens to be X. But we want to find out what the value is. So we know that there are 360 degrees inside of the circle. So if we add all three arcs up and set them equal to 360, we'll figure out our answer. So X plus 114 equals 360. So 2x plus 114 equals 360. Subtract 114. All right, now you should be doing this together on your calculator, not just following along with what I'm doing. Test it out. All right, 2x equals 246. And when I divide by 2, x equals 123. All right. So number 4 looks like it's even more different, but if we notice, we have two congruent arcs, RQ and MP. They have the tick marks. All right, so that means that these arcs are congruent, the red arcs. So if this arc is 67, this arc is 67. But it didn't ask us for RQ, it wants to know X inside. Well, remember that X there, this is actually a central angle. And remember, our central angles are equal to the intercepted arc. So X is 67. No math involved there, just knowing all your theorems. All right, so that was theorem 1. Let's take a look at theorem 2. All right, each theorem is going to be slightly different. So theorem 2, I've got, let me switch some colors here. I've got a diameter, all right, and I've got a chord. Let's see if we can see yellow on here. All right, we can. So here's our chord. Notice that the diameter and the chord are perpendicular. That's a key part. They are perpendicular, so they form 90 degrees. So when we have a situation like this, when we have a diameter and a chord that are perpendicular, what happens is this chord gets bisected, and the arcs, AD and DB, those get bisected as well. All right, so let's write down the theorem. In a circle, if a diameter is perpendicular to a chord, the chord is bisected, and its arc is bisected. All right, so now let's take a look at some of our practicing here. So we have an example here. So now you might look at this and go, but this isn't a diameter. But if we extended it, like we did in brown here, all right, now it looks like this theorem. Even though that's missing, it's still going to be the same theorem because a radius is still part of the diameter. All right, so in circle Y, the radius is 34 degrees. So if I look, I can tell that YC is a radius. All right, so this whole length is 34. But what I'm going to do is something a little bit different. All right, let me take my orange. I want you to draw from YA and to YB. Those would be considered radii as well. So let's label those as being 34. Now, remember, YC is 34 also, but I don't want to put that in my picture right now because it might get a little confusing. All right? It tells us that AB is 60, so A to B is 60. That entire length, A to B, the whole thing is 60. I'm going to kind of draw a line to make us know it's the whole thing is 60. And arc AC is 71. All right, so this arc right here is 71. So now let's take a look. We've got a lot of things we need to figure out here. All right, so they want to know arc BC. Well, if we look at our picture here, we know that the arcs get bisected. So if AC is 71, BC is 71. All right, now they want to know arc AB, from A all the way to B. Just add the two arcs up. 71 plus 71 is 142 degrees. Now they want to know what it is from A to D. Well, if the whole length is 60, cut 60 in half, and we get 30. 60 divided by 2 is 30. How much is BD? Well, it's going to be the same thing. 60 divided by 2 is 30. All right, so now what I'm going to do here, instead of having this whole thing show that it's 60, I'm going to show that AD is 30 and DB is 30. Now, they want to know how much it is from Y to D. So y to d. Well, we do know that the radius is 34. All right, so y to c is 34, but y to d, we don't know. We don't know what d to c is. However, do we notice we have this type of triangle right here? All right, what type of triangle is that? If I put this right angle box in here, we've got a right triangle. So I need to figure out what YD is. I can use Pythagorean theorem to figure out what YD is. If I do 30 squared plus x squared, it equals 34 squared. All right, so if we do Pythagorean theorem real quick, 30 squared is 900 plus x squared, and 34 squared is 1156. I'm going to subtract my 900, so then x squared is going to give me 256. When I take the square root, x is going to equal 16. So that's how much YD is. YD is 16. I'm going to put that in my picture. All right, so if this is 16, the whole length was 34. To figure out what DC is, this leftover piece right here, 34 minus 16 gives us 18 for DC. All right, what I'm going to do here is set up number 11 for you, because it's just like what we did with number 10. All right, we're not going to solve this, but I'm going to show you how to set it up since there's nothing in the picture. Find the length of a chord that is a distance 5 from the center of a circle with radius 8. So find the length of a chord that is a distance 5 from the center. So we've got 5. All right. The center of the circle with a radius of 8. All right, that's 8. So we can put a right angle box in, and we can figure out our missing piece here. So if we do Pythagorean theorem, we'll figure out what x is. If you want to find out the whole length, you're going to have to double it to figure out what the entire length of that chord is. All right, you guys will be able to do that. All right, next page. So theorem 3 and the last theorem that we have to do. All right, this is a pretty easy theorem. All right, so let's take a look here. We've got our picture here. So what we have here is we have some chords, all right, and then we have some other segments that are connecting these chords, all right. So let's take a look. We have UV, and we have RT. Those are our chords. All right. Now, these other segments right here, I'm going to highlight in red. Here's what happens. Those segments form 90-degree angles here. All right, and when that happens, when they form 90-degree angles, when they're perpendicular, all right, these happen to be equidistant from each of those chords, all right? These are the same length. So it turns out that this piece is going to actually be equal to this piece. All right. That would also make our chords congruent to one another. And if our chords are congruent to one another, then remember that our arcs are going to be congruent. All right, so a lot of equal pieces here. But this theorem is basically talking about in a circle, these two blue chords, are congruent if they are equidistant, so the same distance, equidistant, I said distance and distant, if they are equidistant from the center. So all that means is we have a lot of equal corresponding parts. All right, so let's take a look here for these 3 examples. In my picture here, we have an example that looks exactly like this. So if this whole length is 6, if this is 3, this is 3, These happen to be the same length, which would make these the same length as well. So x is going to be 4. Easy peasy. Let's take a look at number 2. They show us that LU and UM are both 8, so those are equidistant. So then that means these chords are going to end up being equidistant. I'm sorry, they're going to be congruent to each other. So if VW is 20, this whole thing is 20, and if YZ is 5x, this whole thing is 5x, set them equal to each other. 5x equals 20, divide by 5, x equals 4. Oh, sorry. And in our last picture, all right, we have our arcs that are congruent. If our arcs are congruent, then we know that our chords are congruent. So they tell us that our arcs are congruent. The tick marks are already there. If our arcs are congruent, our chords are congruent, and then that would mean that these pieces would be congruent as well. So if SZ is x plus 4 and UZ is 2x minus 1, set them equal to each other. X plus 4 equals 2x minus 1. All right, subtract our x. 4 equals x minus 1. Add 1, add 1. X is going to equal 5. All right, so that's it.